What's the derivative of this? I'll use f prime notation now. It's the limit as h goes to 0 of f of x plus h minus f of x divided by h. I keep writing the same thing every time because it needs to get drilled into your head. Right? Go ahead, get a drill out, open it up, force it in there. It must be that limit. What can we do? How can we figure out this limit? One thing we could do is we could write that as e to the x times e to the h. That's a property of exponents. And then once we've done that, we can factor out an e to the x out of the top. And then remember, whether you think about a letter as representing a variable or a constant, it's all in your head. But it is important to realize here that this thing doesn't depend on h. X is fixed when I do this calculation. No h there. Limit of a constant effectively times a function of h. By a property of limits, that can be brought out in front of the limit sign. So it looks like the answer for f prime is e to the x times some constant. But what's the constant? Let's use technology to see if it can help us. So I'm typing e to the x here, but really I'm thinking of it as e to the h minus 1 all divided by x playing the role of h. I'm kind of ignoring the e to the x right there. I'm focused on this limit. I'm letting h go to 0, so pick a window near 0. I'll start with -1 to 1. Or well, maybe -2 to 2. And we'll see what we see. Does it have a vertical asymptote at 0? No, it doesn't. Seemingly. It is undefined when h is 0. There would be a removable discontinuity there. A hole in the graph that the calculator doesn't spend time thinking about. It's just connecting dots. Looks like the limit probably exists, and perhaps it equals 1. Let's zoom in closer. Is the limit of this function? Oh, did I type that wrong? Oh, yep, 0.9 to 1.1. Is the limit of this function truly equal 1? Looks like it is. Trace it. Technically, when x is 0, it's undefined. If I go slightly away from 0, y is very close to 1 on either side. Looks like the limit of this thing is 1. That is true. Can Mathematica confirm it for us? Let's get some practice with Mathematica. For early college calculus students who might be watching this, you can see if you can do this kind of thing on Wolfram Alpha. Wolfram Alpha does do a lot that Mathematica does because they're both created by Stephen Wolfram. Stephen Wolfram's a fairly famous person. He gave a talk once where he's real into technology and math and physics and so forth. I was out of one of his talks, and his technology wasn't working, kind of like we experience sometimes. And I was in the elevator with him afterwards, and I was like, sorry that your tech wasn't working. And he's kind of like grumbles, kind of ignored what I said. But that was my experience with Stephen Wolfram. Anyway, let's give this function a name. Well, let's give this function a different name than f. Let's call it g of h. The symbols you use when you define functions in Mathematica don't matter. As long as you don't use built-in function names, like plot is a built-in function name with a capital P. Don't use that as a variable name, because that's a built-in function. Notice that it's colored black, whereas these letters are not colored black. G is blue and H is green here. The function name is blue and the variable is green. I'm going to type this function of H here. E to the H minus 1 over H. And notice that I used a capital H. That's because if I use a capital E, that's because if I use the lowercase e, Mathematica would just treat it like a lowercase e, not the number e. Capital E is what represents the number e in Mathematica. When you define functions, well, first of all, function inputs in Mathematica always have square brackets, not parentheses. When you're first defining functions, you need an underscore after the variable name. Once you've defined the function, then you don't need an underscore after the variable name. And in fact, if you use it again, you'll get into trouble. There's the function. Mathematica, when it spit it back to me, used sort of a fancy looking E. That can be done by doing escape, escape, I believe. That makes a fancy looking E. That also represents the number E. You can plug in a number. You can plug in a number close to 0 and see what you get. Yes, we are getting numbers very close to 1. But Mathematica can actually compute the limit of this thing with a built-in command called limit with a capital L. The limit of g of h as h goes to 0. This syntax is important. Again, square brackets, not parentheses. The limit must be capitalized. After the function name, you put a comma, and then you type h arrow 0. And I did make that arrow by typing a negative sign and a greater than sign, and it morphed into an arrow. The limit is 1. There's Mathematica's confirmation of it. So it looks like the answer is e to the x times 1, e to the x. Is that true? Yes, it is. The derivative of e to the x is itself. That's actually one of the most important, if not the most important, special fact in calculus. By special, I mean very specialized, not general. The power rule is more general. This is very specialized, one specific function. The derivative of e to the x is itself. That is the most important special fact in calculus, in my opinion. And fortunately, it's very easy to remember. Right? That's very easy to remember. The derivative with respect to x of e to the x is e to the x. The joke goes that there was one professor who this was so important for that other professor that it was on the final exam. It was a one-question final exam. What's the derivative of e to the x? You get it right, you get an A. You get it wrong, you fail the class. Okay, it's very easy, but imagine you're sitting there. It's like, and the professor didn't tell you that was going to happen. It's like, is they trying to play a trick on me? Am I going to get it wrong? No, if you write this, it's correct. Does it make intuitive sense graphically? Here's the graph of e to the x. What we are claiming with this function is that no matter what x is, could be here, could be here, could be here, could be here. No matter where x is, the slope of the tangent line is the same numerical value as the second coordinate of the point. So this second coordinate right there, when x is a large negative number, is close to 0, but positive. The slope is close to 0, but positive. This negative number for x is still negative, but closer to 0. It's technically greater than that number because it's to the right of it on number line. The slope right there is still positive. That's the output of this. The output of this is still positive, but bigger than before. The slope is still positive, but bigger than before. Once you get over here, x is positive. The second coordinate keeps getting higher and higher. The slope is still higher and higher. Here it keeps getting bigger. It should make some intuitive sense because of that, that if you look at how to graph like this and tried to draw the derivative, that you would get a very similar looking graph. That's not a proof that that new graph is the same graph as the original, but it turns out it is. Now, I didn't draw them to look quite the same, but that was just a mistake on my drawing. What about some other base, like 2? What about 2 to the x? I'm really working ahead here. This is chapter 3 stuff, but these kinds of things do come up in chapter 2 here still. And I'm telling you some things that you're technically not allowed to use, but it'll help us later. You might wonder then in your homework, what can you use? I will get to that. What if f of x is 2 to the x? Or more generally, b to the x? Where b could be e, it could be 2, it could be 3, it could be 10, it could be 17, could be a half, could be pi. B could be any positive number, though we typically want to avoid 1 because 1 to the x is not really an exponential function because it always equals 1. It's a constant function. B is positive and not equal to 1 here. What is the derivative? We can do the same kind of thing we did before. Limit of the difference quotient. That's the definition of the derivative. It's a very similar calculation as when b equaled e. Once again, we can use a property of exponents to rewrite that as b to the x times b to the h. And then that means in the top, there's a common factor of b to the x here and here. That can be factored out. Then with regard to the limit, the b to the x is a constant. It can be brought out in front, giving you b to the x times the limit as h goes to 0 of b to the h minus 1 over h. The product of these two numbers is the answer. We just did the case where b was e, and we saw that that limit was 1. Is that the limit in general? On a calculator, we wouldn't know what to do here because we don't know what b is. Can Mathematica handle it for an arbitrary b? Let me go back up here and change the capital E to a lowercase b. What's lowercase b to Mathematica? Just an arbitrary number, that's all. It can handle it. Can it evaluate that at 1? Yeah. The answer involves b. Can it evaluate it at 0.1? Yes, but it probably is not going to give us a number. Still involves b. What's the limit? What's this new limit as h goes to 0? Log b. Is that right? That looks like common logarithm, doesn't it? LOG? LOG is Mathematica's way of saying natural logarithm. Really? Why? Well, when you get high enough in math, as Stephen Wolfram is, it's like the natural logarithm is the best logarithm to use. And we don't like the French anyway. Let's just call it log. Right? ln is really log natural, French. We call it natural log. Okay, I'm not advocating disliking the French, but it's kind of like that's the best log to use anyway, so why don't we just call it log? And common log, you get thrown in the garbage. Really? Does common log get thrown in the garbage? Well, not by everybody. That's actually natural log of b. This thing right here turns out to equal natural log of b. And hey, when b is e, natural log of e is 1. That's why we got a 1. But the final answer here for an arbitrary b is, I'll put the natural log of b in the front, natural log of b times b to the x. The graph of b to the x when b is bigger than 1 still is increasing in concave up. It looks just like this graph. It looks like the graph of b to the x. It's technically not exactly the same, but it's got the same shape, increasing concave up with the x-axis still the horizontal asymptote as x goes to minus infinity. Same y-intercept of 1, because b to the 0 equals 1. That's still the same graph, and so its derivative still has to have a similar shape. But it's not the exact same function as the original function unless b equals e. That's why e is special. One of the reasons. Not the only reason. So this does mean that, for example, the derivative of 2 to the x is natural log of 2 times 2 to the x. The derivative with respect to x of pi to the x is natural log of pi times pi to the x. Fun, fun, fun. Can we approximate these things? Sure. Natural log of 2 is about 0.693. So this is about 0.693 times 2 to the x. It is important to put the dot in there, by the way, this dot, to emphasize these are distinct things. When you plug in a number for x, you do 2 to the x first and then multiply by 0.693. That's ln of pi. ln of pi is about 1.145. So this is about 1.145 times pi to the x. Actually, since pi is a symbol for a number, you don't really need a dot there. It's understood that you would do pi to the x first and then multiply by 1.145. What about, how about 2 to the negative x? How can I do that if it's a negative x up there? I can use a property of exponents to write this as 1/2 to the x, 1 over 2 to the x, which is the same as 1/2 to the x because 1 to the x is 1. And so the answer must be natural log of 1/2 times 1/2 to the x. Natural log of 1/2 is a negative number. Negative 0.693. In fact, it's the opposite of natural log of 2. Wait a minute, does this make sense? Is this really right? Think about it graphically. 2 to the negative x, same as 1/2 to the x, is not exponential growth, it's exponential decay. The b, when you write it this way, is between 0 and 1. That's exponential decay. It's like 0.5 to the x, it's decay at a rate of 50% per unit time if x is time. So the graph has negative slopes now. Not positive slopes. The derivative has to be negative. Slopes of tangent lines are negative. And they get closer and closer to 0 as x gets bigger and bigger. If you graph this function, it's the original graph reflected over the horizontal axis because of the negative sign, and then also scaled by a factor of 0.693 in the vertical direction. So it's a bit closer to the axis, so to speak. But it is negative. There's f prime of x. Oops. Negative 0.693 times 2 to the negative x. The outputs of the derivative are negative because the slopes of the original function are negative. Those slopes start out at big negative values, just like the value of this function is big negative, and they increase towards 0 while staying negative, just like this function increases towards 0 while staying negative. Let's go back to a physics application. Motion again. This time, instead of free fall, let's imagine a mass on a spring. Where this down here, well, that's ice. This is a very hard, immovable wall. And inside here, we have a vacuum, right? What am I trying to do here? I'm trying to minimize friction as much as I can. Well, guess what? I haven't completely eliminated it because there would be internal friction from the spring. Molecules rubbing against each other. Wait, are they really rubbing against each other? Well, in our imaginations, they are. Technically, molecules are not, they're not made of solid material, right? There's electrons and protons and electron clouds like in quantum mechanics and stuff. Oh, okay, I forget that I ever said all that stuff. What's going to happen? We're going to grab this mass, pull it a bit this way, and then let it go. If friction is minimized, it's going to go back and forth, back and forth, back and forth, back and forth, oscillate, basically with a constant amplitude because of the lack of friction. Technically, if there's no friction at all, it's going to keep going back and forth with the same amplitude forever. If the equilibrium position, if this is a positive x-axis here, and if this is x equals 0 right there being the equilibrium position of this mass, it's possible that x as a function of time could be, for example, a sine function. Well, actually, if I pull it to the right and then let it go, it would be a cosine function. If I hit it with a hammer right away, then it could be like a sine function. Let's go ahead and pretend that it's cosine, that this graph of x versus t represents the motion of this mass back and forth. Don't be confused by the fact that in this picture, x is horizontal, whereas in this graph, x is vertical. It's okay. I mean, I could draw the graph sideways if I wanted to, but we're not used to drawing sideways graphs. So live with it. Okay, x starts out at 1. When t is 0, it's like I'm pulling the mass 1 meter to the right. This is a big mass, big spring, not a slinky. Letting it go from rest, the initial velocity is 0 because the slope there is 0. The mass is going to start traveling that way, go through the equilibrium position at x equals 0 when t is pi over 2, about 1.57 seconds. It's kind of a slow moving mass. It takes 1.5 seconds just to get back to equilibrium. It's not going to go back and forth really fast here. Then x becomes negative, and I'm assuming it doesn't hit the wall for simplicity. Goes down to a position of -1 by the time we reach pi seconds. Then it goes back the other way, reaches equilibrium at 3 pi over 2 seconds, and back to where it started after 2 pi units of time, about 6.28 seconds. So it's going to reach equilibrium at 3 pi over 2 and then come back to where it started by the time you reach 2 pi. We're assuming it's cosine of t for this, just to keep it simple. Could have a different amplitude, could have a different period. We might need to do a transformation of this graph to get the exact right graph. But for simplicity, assume this is the case. We might wonder, what's the velocity, for example, at time 1? What is the velocity at t equals 1? It's the derivative. F prime of 1. There would be a limit as h goes to 0 of f of 1 plus h minus f of 1 divided by h, which would be a limit as h goes to 0 of cosine of 1 plus h minus cosine of 1 divided by h. Now, can this limit be calculated? It actually can be. I'm not going to calculate it. It can be done using trigonometric identities, like for the cosine of a sum, and some tricky algebra. Instead, what I'm going to do, though, is something more related to your homework. I'm just going to approximate this when h is small. For example, what if h is 0.001? These should be approximately equal. Are they? Use your calculator. Well, I'm assuming this is going to give us the right answer. Let's see how it works out. Make sure you're in radian mode. If you're in degree mode, switch back to radian mode. I am in radian mode. Cosine of 1.001 minus cosine of 1, all divided by 0.001. H, I'm taking to be 0.001. What should it be? It should be negative, because that slope right there is negative. The velocity is the slope of the tangent line. This should be negative. Nope, about negative 0.84. What would the units be? If the units for position is meters and the units of time is seconds, this would be in meters per second. Let's go ahead and assume that. This is in meters. This is in seconds. Then this would be in meters per second. It's negative, telling you that you're traveling in this picture in the negative direction to the left. At a speed equal to the absolute value of the velocity, positive 0.84 meters per second. The negative side tells you you're traveling to the left. Here's our last thing to do today. Is there another way to figure out the answer here? If you know it, don't say anything. What is the graphical derivative of this? What does it look like? The slope starts out at 0, so the derivative must start out at 0 in value, then become negative. I'm drawing the derivative now. Be most negative right about here, then go to 0 in value when you reach here. T equals pi, because the slope there is 0. So the derivative has to go down, then back up, and reach back to 0 when t is pi. How far down does it go? It turns out to go down to -1 before going back up to pi. The slope right there is -1. And then it goes like this. It becomes positive because the slope becomes positive, reaches a maximum of +1 at 3 pi over 2, and before coming back down. What function is that? It's the sine function reflected over the horizontal axis. I claim this is approximately negative sine of 1. Is it? Negative sine of 1. Yes, approximately. Not exactly, because with the derivative, I was doing an approximation. That is the true exact velocity at time 1. This is really exact. This is really an approximation. They're approximately equal to each other. What this is illustrating is the fact that the derivative of the cosine function, I'll go back to using x here, is the opposite of the sine function. It also turns out the derivative of the sine function is the cosine function. As far as your homework goes, though, what you're mostly doing is stuff similar to what you did today, except you're thinking about derivatives in the abstract and not necessarily physics. You're still thinking about derivatives giving you slopes of tangents. You're still figuring out slopes of secant lines. You're interpreting those things as rates of change. You are still thinking about plugging in small values of h close to 0 to approximate derivative values. We didn't actually calculate the limit, we approximated it. The actual limit turns out to be that, but that takes proof.